Hello, it's YousefZadeh, and in this session we discuss state machines, or the rise of state machines, if you know the movie. So let's introduce ourselves. Maybe Laura first.
Yeah, hi, I'm Laura Kalbag, and I do developer and designer relations at Stately.
My name is Matt Pocock, and I'm a developer at Stately.
I'm Farzad YousefZadeh, and I'm a front-end engineer at Epic Games.
Yeah, so it's great to meet you. And before we go to the first demonstration, maybe it's good to discuss state machines a little bit. So, what are state machines? How do you define them? Why should I care? What's the point? Why do we have this session? So
well, don't take all the talking points from my talk.
No. Just to give some idea to people, like what to expect from this session. Why should they stay watching us?
Laura, you want to take this?
Sure. State machines are a way of modeling something, and we primarily use it in our apps to manage state at the very simplest level. And Xstate is a really cool way of using state charts, which have more capabilities than state machines, to be able to manage state and visualize it as well. So you can do it from a visual perspective as well as in your code, and your visualizations are executable. So it's very powerful.
Yeah, it's tremendously powerful. A lot of what my talk is going to be is about how state charts can help with legacy code, especially, and helping code kind of speak for itself. Because often code can, especially with complex control flows and complex side effect management, code can be really, really hard to read and hard to decipher the intent. Effect management code can be really, really hard to read and hard to decipher the intent of, especially when there's no one in the organization who's able to speak for it. So that's kind of what my talk's going to be about, and I can't wait to show it to you.
Cool. So
yeah, I can also add to this to the discussion. So one way to look at the state machines and the state charts is that they're I wouldn't say simple, but a very, very powerful way of thinking about modeling the solution that you're offering to tackle some problems technically. And that means if you're dealing with something complicated, the state machines are definitely the key to go. And they're a way for you to take a snapshot of every step of your application through its lifecycle and be able to call that with like a unique name. That's what we call a finite state in this world. And my talk would be about the actor model, meaning that you could zoom out a little bit, and instead of focusing on those units in your application modeled in the state machines, you can now orchestrate them to think about the entire application logic and the scenario.
Yeah, so stay tuned. We will have a lot of content waiting for you, and I guess it's good time to move to the first section by Laura. So first demo, here we go.
Hi, my name is Laura Kalbag, and today I'll be introducing state charts and state machines. If you've come to this session thinking, help, I don't know what these are, that is what I am here for. Because really, I was in your exact position just a couple of months ago, a real state machines and state charts baby. And what follows is what I've learned over the last couple of months, explained in a way that I can understand. As a person who has no background in computer science and absolutely hates any kind of unnecessary complexity. Designers and collaborators can rejoice, because state charts are a visual language. So appealing, isn't it? They're used to describe the states in a process. You may have used similar diagrams in the past to design user flows, maybe plan databases or map your app architecture. State charts are another way of using these boxes and arrows to represent flows. But with Xstate, these flows are also executable code that can be used to control the logic of your applications. If you were going to draw a state chart for the process of a dog, yes, a dog, there are two states that would first come to mind: asleep and awake. A dog is always asleep or awake. The dog can't be asleep and awake at the same time, And it's impossible for the dog to be neither asleep nor awake. There's only these two states, a precisely limited finite number of states. And I'll come back to that finite bit in a minute. The states in state charts are represented by these rounded rectangle boxes. And how the dog goes between asleep and awake is through transitions, which are symbolized by an arrow pointing from one state to the next state in the process. Transition is caused by an event that results in the changes of the state. And these transitions are labeled with their events. Transitions and events are deterministic. Deterministic means that each transition and event always points to the same next state and always produces the same result from that given starting condition every time the process is run. Another way of putting it is that dogs never wake up to fall asleep or fall asleep to wake up. It is always going through those states in that same predictable order. This tiny little dog process, with its two finite states, as I mentioned earlier, and two transitions, is a finite state machine. A state machine is used to describe the behavior of something, anything. The machine describes the thing's states and the transitions between those states. It's a finite state machine because it has a finite number of states. Sometimes you'll find finite state machines abbreviated to FSM. That's just people who love jargon. We can safely ignore them. Any process that has states will have an initial state, the default state that the process exists in until an event happens to change that process's state. Using a state chart to describe the process of walking the dog, the initial state would be waiting to walk. And the initial state is represented by that little filled circle with an arrow pointing from the circle to the initial state. Most processes with states will have a final state, the last state, when the process is finished. In the dog walking state chart, the final state would be walk complete. And the final state is represented by a double border on the state's rounded rectangle box. And so between the waiting and the walk complete states, we'd have the on a walk state. And you transition between waiting and going for a walk with the leave home event, and transition between the going for a walk and walk complete with the arrive home event. Compound states are where state charts really start to shine compared to the other charts we might be used to. And they're one of the features that makes state charts capable of handling way more complexity than an everyday state machine. So a compound state is a state that can contain more states, also known as child states. And these child states can only happen when the parent compound state is happening. So let's have a look at what an on a walk compound state might contain. First off, compound state symbolized by a rounded rectangle box, like any other state, that acts as a container for its child states and is always labeled with its own state as well, so you know what state it is. In the on a walk state, there could be the child states of walking, which would each have their own transition events. And I know that this is starting to look quite busy at this point, but actually if you look at it carefully, everything is quite simple. It has its states, each state has its transitions to the other states. All of these states exist inside the on a walk state and as part of the overall dog walk state chart. A compound state should also specify which child state is the initial state. In the on a walk compound state, the initial state is walking. An atomic state is a state that doesn't have any child states. So waiting, walking, walk complete, walking, running, stopping to sniff good smells, all of those are atomic states. The on a walk state is the one that's not an atomic state because it has child states. Can't be an atomic state if it has child states. Parallel states allow us to get to even more complex processes. So a parallel state is a compound state where all of its child states, also known as regions, are active simultaneously at the same time. The regions are separated inside that compound state container by a dashed line. And inside the on a walk compound state, there could be 2 regions. We'll just do 2 for now. You could have loads and loads of regions in this, but I think for this case, for the size of the slide and the screen, I think it's important that we just have 2. You'll see why. One region contains the dog's activity child states of walking, running, stopping to sniff good smells. That's the state that we looked at before. And the other region contains the dog's tail states of not wagging and wagging. So the dog can walk and wag its tail, run and wag its tail, or stop and sniff while wagging its tail. It can also do any of these activities without wagging its tail. The states in each region happen simultaneously. Both regions should also specify which child state is the initial state. I keep going on about these initial states, but it's the thing that I forget the most. In our tail region, the initial state is not wagging. A self-transition, it was when an event happens, but the transition returns to the same state. So the transition arrow exits and re-enters that same state. So if we're going back to dogs again, because dogs are great, in a dog begging process, there will be a begging state with a gets treat event. And for the dogs who kind of love their food, no matter how many times you go through that gets treat event, you know that the dog is going to return to its begging state. And the initial state, of course, begging. One of the benefits of state charts is that in the process of putting a state chart together, you explore all of the possible states in your process. And this exploration will help you avoid bugs and errors in your code, as you're more likely to cover all of the eventualities. And because your state charts are executable, they can behave as both the diagram and as the code. So cool. Making it less likely that you'll introduce differences and bugs when you're trying to interpret between the diagramming and the coding environments. No more throwing things over the wall. There is no wall. So let's have a quick look at how you might go about planning a state chart. And you'll get some really good insight into this in Farzad's talk later as well. To draw a state chart for a login machine, start by listing the basic events in the process. So generally, these will be the things that your login machine will do. So just to start, really simple, log in and log out. And then list the states that exist as a result of those events. So we've got logged in and logged out. And once there's some events and states, there's the beginnings of your state chart. See, got my little initial state going on there as well. Don't forget it. And in this case, the logged out state is the initial state, because any new user would come to the login process logged out. You don't magically arrive at things already logged in when you've never even heard of them before. Some login and log out processes will log out an inactive user after a fixed length of time, like a kind of security measure. We could use delayed transitions for this. So before I get directly into the delayed transition, first we'll make our logged in state into a compound state. And because we'll only keep track of whether a user is active when they're actually logged in, we can't do that when they're logged out. The child states of our logged in compound state are active and idle. The user is either active or idle. The initial state of the logged in compound state is active, because it's safe to assume that if a user is just logged in, they're active. And the event on the transition between idle and active is when there's activity, because we know a user is no longer idle if there's some activity. And we can use a delayed transition, what I mentioned before, between active and idle, because we'll determine the inactivity as a lack of activity for 1 minute. The delayed transition is labeled with after and a fixed duration. And that indicates how much time should pass before transitioning to the next indicated state. That's what makes it a delayed transition. We'll also use a delayed transition of 3 minutes following the idle state to transition to an auto logged out state. If the user remains idle, that's when we'll log them out. And that will be the final state. A state chart is used to set off actions in the system outside of the state chart. Actions are also commonly known as effects or side effects. And side effects sounds like weirdly negative or unimportant, but it's actually the whole point of state charts. The whole point of state charts is setting off actions. You actually want to use these state charts to do something in your code. An action on a state is included inside the state's container with an entry and a slash, or an exit and a slash label, depending on whether the action should be fired on entry or on exit from the state. So in the login state chart, there's an entry action on the idle state to warn the user they may be logged out. So that's the position when we'll fire off an action to warn that user, yeah, you might be logged out if you stay inactive. We're all used to seeing those dialogues, right? So why would you use state charts for state management? Well, for one, state charts make it easy to understand just the small pieces of logic as equally well as you understand that greater whole logic of your application. State charts can do complexity really well. So that works really well with the small to big. They scale really easily from your tiny little machines, which you'll see I make a lot of tiny little machines, to machines inside machines that match the complexity of your application. You're doing state management anyway, so why not formalize it in a way that gives you an overview and a detailed view and can handle that complexity? Because whatever you're building, you're handling state. Whether you're handling it well is a different matter. And state charts are understandable by the whole team. This is one of the reasons why state charts really appeal to me in the first place. I'm a designer and a developer, and I fundamentally believe that we build better applications when every discipline is included from the start of a project. That way we gain the benefit of everyone's expertise. And if your project manager and your designer and your developer can all collaborate on your code without requiring any translation between them, I mean, isn't that the dream? So you can find all of the examples from this talk as actual machines in XState on the Stately registry. If you go to the registry, if you follow that link, you'll be able to find me. You type my name in, Laura, probably the only Laura on there at the moment. Probably, hopefully. If you are a Laura and you want to join, please do. And so you can search and you can just find my little examples up in there. Thank you. And if you like my talk, just you wait until you hear Matt and Farzad's talks. They're going to get into the really good stuff.
All right, so let's move on to the discussion. Thanks a lot for the introduction. I think I learned a lot. I hope other people picked up a lot of concepts and ideas as well. Let's check out some comments. I guess that's kind of obvious. It's good that Schrödinger having a dog, and we were discussing that why do you use dogs as an example instead of cats? But cats are not deterministic. That was the point.
Yeah,
So
they're far too unpredictable.
Nothing finite about cats.
Yeah. So, again, we have this Finnish audience that's not so excited about asking questions. So, does anyone have something in mind to ask, or?
I've got a couple of questions that I could ask Matt and Farzad related to my talk. When you two wanted to learn about state machines and state charts, how did you learn about them?
Oh, that's a good question. I think what I wish I had was this talk, actually, to explain things in a kind of visual formalism, actually, and explain how these things visually sort of match up to each other. I mostly did it just by making a ton of mistakes, usually the way a lot of people learn most things. I really, really liked what you did about laying out the events that your app that can happen in your app first, or in the behavior that you're trying to model, and then laying out the states afterwards. I think that's a really great way of doing it, and how I felt sort of naturally made the most sense to me.
Well, I'm pretty sure that I learned that from watching a video that you did, because that's the great thing that working with these really clever people at Stately is that I've been able to learn from the people who understand it the best and be able to pick up the elements that I can get from you, but also because sometimes I feel like I'm just a bit of a designer head, like I'm really visually focused. It's one of the appeals of statecharts to me, and one of the reasons why I think that they could be so useful as a collaborative tool, because the designer part of me and the developer part of me really gets how it works. But the designer part of me is what really just loves having that visual representation, because nearly everyone gets the idea of boxes and arrows. We understand how these flows work. And so it's so easy to bring anybody in with them.
Absolutely.
So I have a question. So what will you success for someone who has never done any state machine stuff? How to get started? How to get started with state machines? That's the question.
That's a really good question. I would say go to the Stately visualizer and have a go at modeling a state chart for something as simple as a dog, or the process that you use to make your coffee in the morning, or something like that, to just help you get your head around it. And when you have any questions, because you might do like our documentation, which I am trying to improve for XState, isn't quite there yet. I want to make it easier for people who are as beginnery as me. But if you go to the Discord that we've got for XState, I think it's actually called the Stately Discord, then you can ask any kind of question in there, and there's the most helpful and wonderful community who will help you with any kind of question you have. No question is stupid. Everyone is treated kindly there.
Yeah, well, that's a good starting point. So I don't know if you have any more questions, or shall we move to Matt's demonstration? What do you think?
Can't wait to watch Matt's talk, so I'm looking forward to it.
Go, baby.
Got my notebook ready, got my pen.
Yeah, let's go.
Okay, lovely. You can see me, right? I'm just going to make this full screen. Beautiful. Okay, I'm here to talk about making legacy code delightful with state charts, which is a kind of a tough problem because legacy code is everywhere. You know, it's part of the way that we create value as developers is we sift through this code that we've never seen before, that no one knows what it does, and we work out what it does, right? And legacy code is different from unknown code. It's different from code that no one knows what it does. It's code without an organizational advocate. It's code where someone who wrote it has either moved on, or they've disappeared, or they're on a different team, or something has changed. But legacy code is incredibly tough to deal with. And I'm sure you've been in situations, I know I have, where you've just been left alone to figure out this incredibly tough thing. And usually legacy code gets rewritten or destroyed completely. And the thing about legacy code is that it's just code, but it's code where you don't understand the intent. And when you do understand the intent of legacy code, what it's trying to do, what behaviors it has, it stops being legacy. Now, legacy code in React, there's a million different ways that you could create legacy code in React. Anyone can write weird code or bad code or strange code. But I want to focus my attention on one particular part of React that does a lot of heavy lifting and can result in a lot of unreadable code, and that is the useEffect hook. The useEffect hook is really taken on the brunt of managing pretty much all side effects in vanilla React. And side effects, as Laura mentioned, kind of get a bad rap, but side effects are, talking to the database. That's technically a side effect of a pure function. Side effects are the things that your app does, and this used to be spread out in component lifecycle methods, but these are really no longer in vogue. So useEffect is really the place that we do all of our side effect management and orchestration. And let's look at an example here. And when we look at this example, I want you to kind of imagine really picture the way that you're processing this code. What are you looking at first? How are you breaking it down? What's your process for taking legacy code and turning it into code? So we have this here. What I notice myself doing, first of all, is I look at the names of things. We have this Pokemon fetcher just here. We have, what I like to do is look at the props interfaces first. So we've got an ID coming down, and we have this Pokemon data and type data. So we understand all the dependencies of our process now. We have an ID, Pokemon data, and type data. Cool. Let's go on to the first use effect. The first use effect here, if there is Pokemon data, then we fetch the Pokemon type with Pokemon data.typeID and then set the Pokemon type data. Okay, so Pokemon data starts out undefined. So this can't be the first thing that happens. Okay, let's go on to this next use effect. This use effect relies on the props.id, which I assume we always have, and then it sets the Pokemon data. Okay, we've got it. This thing runs first, and then this thing runs first. What's wrong with this process? What we just did there? What feels bad about that process? Well, you notice that the first thing that we had to do was scan all the dependencies. We had to go, what is in this kind of dependency soup that we're eating from? We have the ID, we have the Pokemon data, Pokemon type data. All that stuff could be influencing our app. Then you need to dive into all the implementation details. You need to look at all of the dependencies of the use effect. You need to look at what they're doing just in order to understand what the app is doing. And then finally, the intent of the code becomes clear. You have to dive into the implementation details first, and then you understand the intent. So, is this process delightful? No, it's crap. It's really rubbish. Because you really, it just takes a long time and a lot of taxing mental effort. And what you need to do is so abstract and so disconnected from what you want to do, which is just understand what this code is doing. So let's do it again, but harder. With this one, we're looking at some code which is to do with an async load video. This is the behavior that I made here. Notice that it's in a loading state first, and then it loads the image, and then when you mouse over it, the image fades away and the video plays. And when you mouse away, the video stops playing, kind of like a Netflix thing. If you want to, you can pause this talk, and you can go to my GitHub repo, which is Matt Pocock React Finland talk, and you can have a look and see if you can work out the intent of the code. So ready? Pause the video now. 3, 2, 1, go. We're back in the room. Let's do the same thing as we did last time. Let's look at the props declarations first. We have video source, background image source is hovered and is on screen in the props declarations. Then we have whether the video is loaded and the image is loaded in the state, and we have a ref. Okay, so is hovered and is on screen seem important. Then we can jump to the end here because we have a return statement, which has, if the image has if the image hasn't loaded, then return this loading div here. Okay, but if the image has loaded, then we can safely show the image, and it's hidden if it's hovered and the video has loaded. Okay, so we've got this sense of the image loading being important and the video loading being important. I wonder how those flick to true, because here they start as false. So we have a use effect here. This is the first of 3 use effects we have. Props.bg image and props. So if those are true, then we set the has image loaded to false. Then we load the image. So this is some async load image stuff, it looks like. And then we set has image loaded true when the image is finished loading. And the dependencies are props.bg image source and props.is on screen. So if either of those change, then this reruns. You see? All right, so we're looking at this now. This is pretty similar to the background image source that we looked at before, except it's loading a video. And the last one here, now if props.is hovered and there is a video element and the video has loaded, so this is coming from the ref, then we play the video, and then we return. So we return a callback saying to pause the video. So under these conditions, the video should play, but then we pause it afterwards. Interesting. So we have the process, I think, which is we load the image and the video at the same time. But if they're changed, if props dot is on screen, then it sets it to false, I think. And if props dot is hovered, then we play the video. As you can see, this problem scales with complexity. As the app gets more complex, the use effects get bigger. The control flow is harder to work out. And I only really sort of doubled the complexity there, like twice the amount of dependencies, twice the amount of use effects. And how do you usually mitigate it? Right? What strategies do we usually use? We usually use things like inline comments. We usually say, okay, this comment here applies to this use effect, and it does the thing and it describes the conditions. This is pretty good. Sometimes code comments are completely necessary. Sometimes they're they absolutely save a line of code where you just couldn't understand it at all. But really, you're just improving the flow that you've had already. The flow that we've described here is bottom up. You're having to read the implementation first and then understand the intent. But really, inline comments just sort of make that process faster instead of changing it completely. So, and of course, inline comments can go out of date. You can basically just have a comment there that was written 4 years ago and the code changed multiple times since then, and it's completely out of date. The kind of same rule is true for external documentation, for docs that are external from the code. Although they can be kind of useful, like if you have a Markdown file understanding that describes a whole set of code coverage and that sort of thing, then you do get a top-down view of what is changing in your application or what your app is supposed to do. But most of the time, people don't update those in pull requests, or they're even further abstracted away from the code than inline comments are. So easy to notice when you don't update a Markdown file or something similar. And the third way to make this process easier is through abstractions. Hooks and use effect is really great for this, because you could potentially just wrap a whole bunch of those use effects into a use load video hook. And when the video has loaded, then you can show that on the screen. So again, I think this is the second best way to tackle this problem. But really, you're still sitting in the same dependency soup. You still have to track video source and when it changes, and track is on screen and when it changes. And you're now splitting out the problem into multiple modules, which can be good and can be bad. So abstractions, I do think they're quite a good way, but again, things are still bottom up. It's kind of like an inline code comment, but better, more modular. But I think we can do better than this. The solution that we'd need, if we were to find a solution, would be a kind of top-down documentation approach where you had the intent come before the implementation, and that never got out of sync with the code, that was always guaranteed to be in sync. And that solution is statecharts. So what I've done is I've built if we go all the way back to this here, I've built a statechart implementation of this. You can see that there are multiple finite states that we can understand here. There is a finite state when it's loading the image at the start. There's a finite state when it has the image. And then there's a state when it's hovered and unhovered. Let's have a look at what that looks like in a state chart. Boom. So this code is, as Laura described, runnable. It's an executable state chart. We have specific events in here for when the video source changes and when the image source changes. And we have other events for when the image has finished loading. And when it has finished loading, we go into this loading video state. We have mouse over and mouse out here. And we have events for when the video loads and when the video load is complete, and even when the video load errors. And right here, you immediately see the intent of the code. It's right there for you before you've even looked at a line of code. This is the implementation, but it's also abstracted away from the implementation. And really, it's intent first, implementation second. what this means is if there's a bug in in the load video bit here, and you're getting some error message which says, there's a bug in the invocation inside machine video.loading or something. That's a very typical XState error message. Then you know that you don't need to touch anything else inside the app. All you need to touch is this video loading area, and you instantly know how it connects to everything else. So the next thing is explicit events are kind of easier to think about and track than implicit dependencies. When you have these kind of implicit dependencies all over the place, like, these things here, you're just sitting in this dependency soup and you're waiting for things to change. When props.is is hovered changes, how do you track that through your application? What happens when, you're on this one, for example, and is on screen changes, but the video source doesn't change? It's really, really hard to derive intent from those changes. Whereas intent in these events is incredibly easy to derive. You understand instantly what these events are, and you understand immediately kind of what they're reporting on when it's built well. So they're so much easier to track, and it makes understanding the intent of legacy code a lot easier. And finally, the most important thing is that the diagram doesn't represent the code. The diagram is the code. It's runnable. There's no separation at all between your comments or the documentation and the code. Like, we rely on documentation so much for the libraries that we rely on every day, React and XState and all of these things. If that documentation goes out of date, it can be disastrous. It can lead to a production bug. So why don't we treat the documentation that we produce ourselves with the same vigor? The really exciting thing for me about this is that it turns your code from just code into code that's statically analyzable. You can really just use tools to peer into your code, understand everything that's going wrong or going on. And at Stately, we're building tools to help you do that and to make these incredibly rich experiences so that you can make legacy code delightful. The main thing that comes out of this, we'll probably talk and answer questions about this in a minute, like all of the implications of statically analyzable code. But the main thing is you produce code that can speak for itself, code that can allow you to read into its intent instantly without you having to do any extra work, without anyone having to do any extra work. And it democratizes the consumption of code so that you can, anyone can read your code and understand what it does. If you build a system for someone and then your team gets, sent away or something, and then you have maybe a non-technical person who's just dealing with all of this code, surely they want to understand it and read it, And if they're not coding people themselves, they want to understand the intent of it. And this is the kind of thing that XState and statecharts enable. And that's me, really. I'm so excited to talk about questions for this because there is just so many implications of being able to peer into your code and understand what it's doing and how it works and get all of that on the table.
All right. Thanks for the great talk. And that's difficult because we do online conference, so you don't get applause from the audience. That's at YouTube. It will be weird if everybody was clapping their hands at home.
I appreciate it.
We can do that as well. But now we get questions. So what kind of possibilities or tools do you see or see for designer-developer collaboration with the statecharts?
This is where we're going with Stately. I can, a lot of design tools these days are componentizing. Like Figma is currently starting to be built around components. Modules is starting to be heading that way too. And if we start seeing statecharts move that way, then it's going to be really, really exciting, I think, for what we can do. And I've been even thinking a lot about using statecharts for prototyping too. If you can attach like a very basic layout to a state and you understand what it's doing, then you add buttons for moving between, for firing events and things like that. There's so many cool possibilities here. Yeah.
So let's see what people are saying. So it's like great talk. Oh, there's clapping and nice and clapping. So it's a lot of people are clapping at home right now. But this will ask more questions. Or do you have some additional thoughts on the topic to discuss?
Well, what do you guys have, Laura and Farzad? You got any questions for me?
Yeah,
oh,
I
no,
was
we got question. Wait a
Oh.
moment.
let you and Matty go first.
How easy is it to start replacing things in legacy code, one function component file at a time, while keeping other parts of the app legacy?
I mean, if you don't understand the intent of what a piece of code does, you probably shouldn't be changing it. When you do understand the parts of legacy code, is that you can model small things with state charts. You can model small behaviors, and you can start to reclaim parts of your app slowly with state charts. It doesn't need to be a big change. And so, yeah, it's about hacking down the weeds, like how else do we do these big refactors, like little bits at a time?
Yeah, it's a bit like with this, like the first thing I like to do sometimes when I have to work with code I don't know, that doesn't have tests, I start writing tests. I test the code so I can validate if I understand the code.
Mm-hmm.
And I guess eventually when you test enough, you could maybe start extracting some logic and maybe start pushing it around. So it's sort of, I guess the point is that when you work with legacy code, it's about understanding.
Yep.
Like understanding what you're dealing with, and then replacing the old thing with a new thing that's easier to maintain.
Well, that kind of pushing around, would you call that process delightful? It doesn't feel very delightful to me.
No, it's not delightful. No,
Yeah.
It's just like improving. It's better to have code with tests than no tests.
Mm-hmm.
But
I would say it's better to have a code that tests itself.
Yeah, that's even better. Yeah. So that will be like the thing to where to go. So Laura had some.
Yeah, I was just going to say that when I was watching your talk, and it made me think that really it makes it a great solution for that idea that everyone says, oh, I don't need to comment or document my code because you can just read it and understand what's going on. And that is so rarely actually the case. And so this is a really great way of solving that problem, is that no, actually, this does make it much more understandable to a much wider audience as well.
For free as well,
So when it comes to testing, so like a lot of people know how to write unit tests and all this stuff, and then you get more complicated things like property-based testing, and so how does testing relate to state machines or state charts?
Well, I can say this. This is a separate talk, but if you think of a state chart like let's say we take Laura's state chart of a dog. You don't need to use that state chart to model a dog. You don't need to execute it you don't need to use it to power the dog. You can use it to assert that the dog is behaving correctly. Let's say that we have some other kind of little dog robot that's written in JavaScript or Node or whatever, and we want to assess its behavior. Well, first of all, we can use that state chart to power our tests instead of our thing, and model-based testing is a really powerful tool, and it's something that XState already offers with XState Test. There's some refactors that we want to do to that library, but I've been using it happily to test backend code before, and it's been marvelous. And front-end code.
Yeah, it's a very underrated, aspect of modeling with the state charts. That is, many people think that they need to model their problems that they have in the code that needs to execute using a state machines and a state charts. But rather, you can just take your understanding and how you perceive the software works, which is usually more flat and simpler than the actual implementation. Write that in a scenario-based, a state chart, because that already gives you the upfront graph. Then you can run automated, integration tests because of that. And David also has a talk that he gave, I think, 2 years ago at React Rally that talks, you don't even have to write the integration test based on the state chart, but rather auto-generate that because you already have the graph when you were thinking about how to model it.
David who?
Yeah.
Oh, that's a David Piano, known in the wild.
I've heard of him.
Yeah, so saying to the audience that if you have any questions, just send them to us, and we get to them at the end of the session. So do you have any topics left to discuss, or shall we move to the next demonstration?
I just wanted to mention something very quickly. Maybe as JavaScript developers or generally working in the web development industry, we don't really see much refactoring or working with other engineers with different technologies. But having worked as a gaming company, people work in the gaming industry with different technologies and different game engines. And working as a web developer amongst other game developers means you really have to show the intent of your code and let other game developers reflect the business in your code and fix it for you. And the state machines has been the way for us to go with that at the company.
Yeah, and I think it's good time to go to the last demo by Farzad. So let's do that and then get back to more questions.
Hi, my name is Farzad, and today we're going to talk about Actor Model, a new mental model to thinking about complicated React applications. Before we jump into the talk, I wanted to quickly just thank the organizers of React Finland for giving me this opportunity again to stand on the stage of this conference and present my ideas. The purpose of this talk would not be to get a hardcore, practical, hands-on demonstration of the implementations of Actor Model, but rather I tried my best to focus on the abstract concepts and try to get the foundational pillars right. Because I believe if we get the foundations right, then it wouldn't really matter what the implementation of Actor Model is and which one we're using. Hopefully, this talk will reach out to the audience that are interested in learning more about Actor Model, and hopefully the resources that I'm going to be sharing at the end of the slide deck will also help you get on running with the Actor Model even more. As I mentioned, my name is Farzad. I'm a senior front-end engineer working at a company named Epic Games. It's a gaming company, but I'm a web developer. I'm not a game developer myself. I'm really passionate about the state machines, state chart, and specifically talking the XState library and the stately AI team. You can reach out to me on GitHub under github.com/Farzgate or Twitter /Farzad_YZ. If you're also keen to check my website, you can go to farzadyz.com. Let's cut to the chase and dive right into the Actor Model. What's the definition of Actor Model? Actor Model is an architecture that's as old as 40 years old. It's an architecture that proposes a really simple yet elegant way of orchestrating logic in your application. In Actor Model, everything is an actor. An actor is an entity that has a private state, can send messages to the outside world, meaning to the other actors, and can also receive messages from those actors. If it receives a message, it has a chance to process that message and possibly change its internal state. And if other actors need to be aware of the change in that state, or at least part of that, then this actor can also send a message to those actors saying that here's the change and here's the new value of the state. In Actor Model, nothing happens magically. If there is a change, it means there has been a message asking for that. And that means everything is quite clear, and the entire integration layer of your application has been brought to the surface. So it means the integration problems can be caught before they catch you as bugs. When you use Actor Model in the context of React front-end development applications, it means when we moved from imperative DOM operations to thinking about declarative and composable components, we are dealing with a tree of components that build upon each other and make our entire application. Similarly, we can think of the application using Actor Model as a tree of stateful bits called actors that are interacting with each other, and there is a root guardian actor on top that's probably spawned at the beginning of your application, and that can dynamically spawn any ad hoc actor to continue with the rest of the behavior of the application. But these two trees don't necessarily map to each other. Not all the components need to know about all the actors and don't even need that. There is a many-to-many relation between components and actors. And this gives your UI a chance to only get notified about the things that it cares about, not the entire store that we see in Redux. And saying that, it means that if you're coming from the world of Redux to actor model. In Redux, the UI subscribes to an entire giant brain store called the Redux store. And Redux then gets the messages and passes that through a synchronous chain of reducers. Each reducer has a chance to change the state and react upon that. And at the end, the new value of the state is going to be notified is going to be sent to the UI again. But in actor model, it feels like we got those reducers, taken them out from the chain of store. Now each of them are one little store. They can interact with each other. They can send message componentry. It's just yet another actor in the entire system. One thing that I wanted to focus here at the beginning of the talk is that with actor model, we learned that integrations are brought to the surface. And integrations matter. Why? Because when the applications grow, when we're dealing with the larger scale applications, not necessarily the number of units, which are the actors and the components in the application, grow, but rather the amount of communication between these units grow. With using component libraries such as Chakra or Material UI, you probably don't build your features by adding new components, but rather building your features upon those primitive reusable components from those component libraries. You can do the same with actors. You can create so many primitive reusable actors and then build your features upon those, instead of having to create and adding more logic by feature to your application. Guillermo Roche once tweeted something very famous, saying that you have to write tests for your application, but you don't have to necessarily write too many tests. You can just mostly focus on writing integration tests. And this is very important because now with actor model, integrations are brought to the surface, they're exposed, they're now very predictable, they can be traced, and you can have a time travel through that. And you can even see the sequence diagram or the user flow that the users have taken into your application. Imagine that when the users are dealing with a bug and they're filling a crash reporting, or you have a crash reporting service that's automatically, issuing these problems in your crash reporting service, you only have to record the messages that have been passed as a sequence diagram in your application and then automatically run some integration test against them to find the problem in a chain. Meaning that if there is a problem in one of the units, since units are really isolated and narrowed down, it's usually very quick to find those problems. But if an integration fails, it means you have to prepare an entire environment, find the relevant actors, put them in the right order, step into that, go one by one, and find the outlier behavior right there. So integration problems are much harder to diagnose and debug than unit problems. And hopefully with the use of actor model, you can bring that to the surface and make it more predictable. Step one to using actor model for modeling the application is to being able to identify different concerns in your application and assigning an actor to those concerns. Let's take a very simple React application for an example here. Let's say that we have a Markdown renderer application. There is a Markdown editor on the right side, and there is a preview of the compiled Markdown to HTML on the left side. There's also a login, signing and sign out system. If the user has an active session, we retrieve the user info, show it on the top right sidebar of the application. And the users can retrieve these already saved sources in the database by appending an ID in the query parameter in the URL. If there is an ID, then your application need to pick it up, talk to the database, fetch the content, prefill the editor with that. If the user presses the compile button, that means the editor content, assuming that it's a valid Markdown, needs to be compiled to HTML, and then the preview section needs to pick it up and show it as HTML to the end user. And if the user presses the save button, the current value of the Markdown editor should be saved into the same database that we read the sources from in the beginning. Now, the user stories that we just thought about in this simple example, they can be reduced to a set of concerns, and each of those concerns can be categorized under a responsibility of one actor. Starting from reading the source ID from the query parameters and talking to the database, attempting to get the source of Markdown for that particular ID, and then if that's successful, getting the source, notifying the editor that here is the editor content. That can be one concern. A similar concern is when the user presses the save button, then you're going to have to get the current editor value and talk to the same DB and save it there. So these two are very similar. They can be categorized under the same concern. We can assign a source actor to that. Similarly, previewing the parse Markdown can go under a preview actor. Parsing the Markdown source and prefilling the editor with the retrieve source can also go under the editor actor. showing the toast messages can have its own notification actor. Signing in and sign out can obviously be categorized under an authentication actor. But how would these actors play out in the field to make up the entire application logic? Here's where the sequence diagrams or the user flows or the scenarios coming. And an analogy that I'm in favor of for applications is that applications are like movies that have scenarios. In this case, applications are movies that have multiple scenarios. And the user of your application, based on some criteria, can take one of those scenarios and use your application using that scenario. So it's like your application is a living movie that has different scenarios, and users can do that. And with the actor model, getting these sequence diagrams or user flows out and learning them is going to be very predictable and easy. For example, in this sample application, you can see that reading the ID and retrieving the source from the database can have this sequence diagram. As you can see, there are like the identified actors are on the top of this sequence diagram. And the only actors that are playing the role in this scenario, the scenario of reading the ID, talking to the database, and getting the source, are the source actor, notification actor, and editor actor. Assuming that there is an ID in the query parameters, source will read that from the URL, send a message to itself saying, I found an ID. Then it reads try to send the ID to the database, sending another message to itself that, hey, you have to read it from the database. Then if the content from the database has been retrieved successfully, it sends a message to the editor saying, hey, I received this content. You now have to pre-fill it in your value. But if something goes wrong while retrieving the source content, it sends a message to the notification actor saying that I wasn't able to retrieve the content that the user was asking for. So the notification actor can act upon that and show a fancy toast message for that. Similarly, for the scenario of saving source, we can also have another sequence diagram. With saving, if the user presses the save button, it means the UI now needs to send a message to the source actor saying that the user has pressed the save button. In response to that, source will tell the editor that, hey, I want to get your content. And editor will also send a message back to source saying that, hey, here's my latest content. Source will also get that content, send a message to itself back saying that I want to save the content in the DB. And now the entire side effect of sending the post request to the database is going to be performed here. If that fails, source needs to notify the notification actor with the error message. So that will be shown. If it's successful, source will send a message to itself saying that, yeah, it was successful. So it's your chance to save the ID or any other metadata you want from the updated source in your internal private state. It will also send a message to the notification system saying that, hey, I was able to save it successfully. So it's your chance to show like a green alert or something like that, telling the user that it was successful. Another similar scenario is editing the Markdown, only that out of the 6 actors that we have in the system right now, the only actor in this scenario that's playing this role is the editor. The entire editing Markdown scenario consists of only one event, and that's going from editor to itself, saying that my content has changed, getting the value from the text area or input, and then saving it, updating it in the entire internal state of the editor. And another scenario is checking the user session and user info, which involves the authentication actor, notification actor, and the editor actor. So basically, we don't want to get into that because it also has a similar explanation as the previous ones. And one interesting one is also compiling and previewing. In the compiling scenario, the UI will tell the editor that, hey, I want to compile your current Markdown content. Then editor will signal the Markdown editor, the Markdown actor saying that, hey, I want you to compile it now. Here's my latest source. Then Markdown has a chance to compile it now and run a side effect. And if that hits some errors, it has a chance to send a message to notification saying that here's the error message you need to show, parsing failed. Otherwise, it will get the rendered output and send it back to the preview actor saying that, hey, here's the latest HTML that you need to preview. So preview will paint that to the UI for the end user. So you can see that with actor model, it's just basically a sequence of events that are passed between the actors in the system. And it's really easy to read through that. And this also can act as a, these diagrams can act easily as a documentation of the system behavior. So at the end, it would be very, very easy to onboard new engineers to the problem, or even talk about these behaviors of the UI based on the user story is passed from the business level, and talk about the technicalities to the business or non-tech stakeholders without having to get into the implementations or technicalities. Another interesting aspect of using actor model for front-end development is actor model plays really well with feature growth. Well, applications don't stay the way they were intended. They're not always stay feature growth. Well, applications don't stay the way they were intended. They're not always stayed as the proof of concept, right? They will grow, and sometimes they grow really fast in case of, for example, startups or fast-growing projects. What happens here is that if you're using the, let's say that like in our, we assume that we have an application, right? The Markdown render. Let's take that into example again. And now let's say that the project manager has told us that the users want to embed the preview of the Markdown in their blocks, but for the embedded mode, we don't really need any sort of authentication, or we don't need to render the editor at all. Or basically, we also, yeah, I mean, like we don't need the editor and the authentication, right? So those features can be excluded from the embedded mode. But what we do normally is that we just basically, it's enough for us to conditionally not render those parts of the application, or you know, like hide them from the user. It would work pretty fine, yeah, but I can't sleep well at night knowing that the logic of those behaviors is still in the you know, in the application system, and knowing that it's possible just the UI doesn't let you interact with that and trigger those scenarios. And also means that the complexity of the system still stays the same, regardless of no longer needing, you know, all the actors that have to play their role in the system. So we can, with the actor model, we can dynamically change the structure, change the orchestration, put a mode actor in front of the system actor instead of spawning those other actors directly from the system. Mode has a single job. It detects if you're in the normal mode or you're in the embedded mode. If you're in the normal mode, it registers and spawns those 6 actors that we see before in the system registry. Otherwise, if it's in the embedded mode, it only spawns notification, preview, markdown, and source. It excludes the authentication and the editor because they're no longer needed. And that means that you're taking those actors which are no longer necessary to the application behavior, and you're dynamically reacting to what's needed in the application. And that means if a bug happens later on in the embedded mode, you don't have to really go through the user scenarios or sequence diagrams that include the authentication or editor actors, because they're no longer in the system at all. They're not just hidden or not conditionally rendered. They're totally excluded from the logic layer. And that's pretty cool, right? Yeah. Another benefit of being able to dynamically spawn ad hoc actors in the actor model system and to be able to play around with the complexity of the system is that a system with 6 actors, as shown on the left picture, is can have, since every actor in the system, assuming that they have references to each other, can talk to one other, it means that with n actors in the system, the number of unique messages going to another actor as a target is going to be n raised by the power of n. And that means in case of 6 actors in our simple React application, that's going to be 6 raised by the power of 6. And that's in the scale of thousands of unique messages that could be passed technically. But if you reduce it down to 3 or 4 for another mode, it can be 3 raised by the power of 3, so 27 unique messages that can be passed in this case. But like for the embedded mode, we saw that they're only needed for 4 actors, so it's going to be 4 raised by the power of 4, and that's 2 raised by the power of 8, 256 unique messages. So compare a scale of thousands unique messages that could be included in the application layer and the sequence diagrams. Compare that to the scale of hundreds, which is 256. And that means the complexity can be decreased significantly for features that are intended to be lighter than the rest of the application. And it's quite cool. Though it could be a vanity metric, nevertheless, this is still a metric to measure the complexity of the system against that. We're getting to the end of the talk here, and I just wanted to tell you that as a recap, we can think anything can be an actor. Well, if it can send an event, if it can receive an event, and it can have a private state, basically actor has a very thin layer of interface. If it can contain a private state, and if it can send event to the outside world or receive event from the outside world, it means that it can be an actor. And that means actor model is pretty flexible and quite unopinionated about the implementation of your actors. With the front-end development, we deal with quite a lot of asynchrony. We do stuff over the dimension of time. And for that, we model using callbacks or promises, right? And that means if we get to implement promises or callbacks as actors and adapt them to the interface of an actor, it means you can pretty much model anything in the front-end side using actors. You can even like have other primitives such as state machines and state charts as another implementation of an actor, or even an observable as an implementation of an actor. So with actor model, you can really mix and match different types of implementations. You can have more complicated actors to be implemented using state charts, but you can have the naive ones or simpler ones to be implemented just using normal promises, callbacks, or even have observables to be reactive, what have you. So just to recap, the advantages of actor model that we went through is actor model is pretty simple in the sense that it's not really opinionated and everything is a message. Since everything happens through message passing, it means no change will happen unless somebody asks for it. It also helps with the observability of the system. You can understand how the entire application works at the scale by looking at the message sequence or the sequence diagram, as we saw. It's like reading through a scenario and tracing what exactly happened step by step. It's like time traveling magic. There would be no race condition, of course, because actor model inherently tackles the concurrency problems, and race condition is one of those issues with concurrency. Actors are a great approach to concurrency without multi-threading, and they fit very well with the event-driven nature of web, and especially platforms such as browsers. Therefore, an entire class of inconsistencies due to concurrency is eliminated by just adopting this elegant yet simple architecture. There are scalable. Well, we saw that they can build up on top of each other, and any actor can be spawned ad hoc. They work really well with the web APIs, right? I mean, web APIs are either passing messages like communicating between an iframe and the parent iframe, or communicating between the main thread and a worker thread, and they can adapt pretty well. They actually are normally an actor themselves too. Actors are composables. They're really composable. They're really easy to diagnose because they're predictable and everything happens through explicit message passing. And they are isolated logic that are kept outside of the React tree. So you don't have to, deal with the trade-offs of lifting the state up just to make it more accessible to other components, or quite constantly have the dilemma of whether to accept the trade-offs of refactoring some local state to React contents and make it available to an entire branch of components or not. So some other additional resources as promised at the beginning of the talk. Well, you can check these resources. I'll be sharing the slides later on with the organizers, and they can share it through the mailing list, so you can take a look at that. Thank you very much, everybody, and I hope that you took something useful away from the actor models talk. Thank you. Thank you.
Juho, you're muted.
Yes, I was muted. It's like, you're muted. That's the most common expression of this time. But yeah, I was saying that we have to make this clapping a habit. And I hope everybody is clapping at home as well, or wherever they work, wherever they watch. Yeah, people liked it. This was interesting one. John likes this more than UML. It sort of makes sense as well. I don't know if they were teaching UML when you were at the university or wherever you went to study, but it's cool. So I have a couple of questions here. Let's go through them. Are there any issues or gotchas with persisting state from a state chart or later loading it to continue the flow?
I guess I can take that partially, but I think Matt particularly has some experience with doing that practically. Something I wanted to mention as the answer to this question is that XState has this built-in. We have a built-in way to dehydrate and hydrate, or actually, dehydrate and hydrate the state, persist it to some sort of temporary storage, and then bring it back to the scenario and make it live in state. And I think there is an state.from API in the core library for doing that. And I've seen some discussions in the community on the Discord that people are actually using it for very, very like exciting use cases. Matt, do you have anything to add to that?
Yeah, dehydrating state was what actually I was doing earlier. So what... Laurie gets it. So yeah, I mean, there's tons of stuff. The complicated thing about state charts is that they can spawn other state charts. And so when you're talking about persisting and rehydrating, you're not only talking about persisting a state chart, but you're also doing it for the entire actor model that it's spawning too. This is a library concern. This is an XState thing. And this is something that David's actually spending a lot of time on. And David, I think, has a PR in progress right now to be able to do that, to be able to basically take an entire serialized state chart and actor model with all of its initial states and stuff, and just go, boom, there you go, rehydrated. That's really exciting because it solves some issues that we're actually seeing with XState in React as well, which is getting fast refresh, working really nicely with React. Because the thing about XState is that it's sort of a separate process to React. And in order to get fast refresh working, you need to be able to destroy the entire state tree and rebuild it, basically. And that's something that is going to be working very soon. But essentially, the answer to the question, which is, are there any gotchas, is at the moment, yes. But give us like 4 weeks and there won't be any gotchas. This is something that we want to do properly and make a really great experience.
I'm pretty sure you're not supposed to promise anything publicly. But hey, one thing to mention about one thing I wanted to add to what Matt said is rehydrating a state and taking that from there and continuing from there in the scenario doesn't necessarily mean that you're replaying the exact state, because some of the side effects are not, you cannot just assume that they have happened before. Mm-hmm. You can't come back from some of the side effects. It's just a one-way road.
It's this time travel problem. So you cannot take back some.
Yeah, it's a conceptual thing. Yeah, it's a physics problem.
Yeah, exactly. Next one though. So do those actor model charts map directly to events sent between state machines?
It really depends on at what zoom level you're trying to get your sequence diagrams to exactly reflect the implementations. But basically, the more detailed they are, you have a better chance of diagnosing. That's it. I mean, if probably you want to exclude all the messages that went to the self actors, because those are like internal events in the actor. And looking up from like another level, it wouldn't matter. Most of the integration events that matter are the ones that are sent between the actors, because those are the places that the data transformation happens.
All right, I guess next one. So what is the best way to organize communication between actors in React? Invoke spawn in global machine, event bus. What will you use?
This is another thing that we're...
That's one of you two, I'm sure.
This is something we've been talking about a lot actually recently, which is a lot of what XState has been focused on is kind of local component state. It does it really, really well. And you can use it to drive global state in React as well and spawn other actors and things. So the best way is kind of still up for debate. There's two ways. You can either have a global state machine. It's kind of still up for debate. There's two ways. You can either have a global state machine which spawns other actors, and then in there you get to use these techniques which are visualizable, where you can actually from the top machine spawn another machine and then send an event to it, which is quite nice. The other way to do it is you have a machine at the top and then you get React to spawn another machine down the bottom with like a use machine or a use interpret, which is kind of like a use state. And to do that, you just kind of the differences between them is that in the XState one, the parent has a reference to the child. So it can send events to it and it can receive events back from it. Whereas in React, communication is only one direction. It only goes down. So the parent can send, in this sense, it's kind of firing off a function which would send an event to its parent. And so you get into this situation where you're kind of doing a bit of React and a bit of XState, and we don't have a strong recommendation for that at the moment. Currently, both ways work. Both ways are pretty ergonomic. So yeah, dealer's choice, really.
Yeah, I can also add to what Matt said. With the event bus technique, it means you have a root guardian actor that's going to act as the main proxy of the event. So you either want to have a registry in the parent actor and pass the references to any actor to any other actor so that they can also technically try to talk to each other and pass events between each other, or you can just basically pass anything through the parent and all the communication goes from there. So if you later on want to like enforce a sort of validation on like a global validation or something, the guardian is there for that. And if everything is proxied through that, it's much easier. Another thing is it really depends if you want to pass anything, all the messages originating from the UI level to the actors or not, because everything going from the UI to other actors is the ones that React needs to take the responsibility for. And in the talk, I was explicitly sending the messages between the actor, like any particular messages was sent as a side effect of the state machine, but you don't have to necessarily do that. We were recently talking with David about this, that any actor model implementation can afford a very thin layer of subscription. So you can just get notified automatically about the state changes without having to send and receive those messages explicitly, at least. Just ask for the change, not ask for get notified.
All right. There's one more at least. Is it easy to integrate XState with MobXState 3?
I actually saw David receive this question the other day, so I'm going to parrot his answer, which is XState and MobXState 3 sort of do some of the same things, but I don't actually know that much about MobXState 3, so it could be possible, but from David's answer, it sounded like there was a little bit of overlap. So probably it's easy, but because XState really can integrate with anything, but I'm not sure.
Yeah, so it's something to try or exercise to the reader, or how did I put it in the math books?
Clean me after class.
Yeah. So I have one question related to this actor model. So during the past year, I've been working a lot with the web workers and this observables and reactive stuff. So is there overlap with these technologies and actors, or are they the same? Is it the same thing, or how do you see it? This workers and all that.
Okay, getting to the observables. Observables being reactive, they're only one of many various implementations for an actor. They can send events in the pipeline, they can receive through the pipeline, and they can also have their own internal state. So yes, they can be qualified as an actor. And passing messages in web APIs such as web workers, that was also mentioned in the talk. Yes, they're already actors too. Yeah, there's post message in the browser, right?
Yeah, exactly. So I was thinking that I've been doing this actor stuff for 1 year without knowing I've been doing it. So it's sort of.
Yeah, if you realize there's no like way of getting around the global scope and accessing things, implicitly, you just have to use the post message for every little thing. Yes, it's annoying at the beginning, but it just ends up being very, very predictable at the end.
Yeah, there's one more question. How far can you take statecharts to backend the database? What's the limit?
Well, I even take it to the bed if that's an answer.
Yeah,
but we are discussing to see what are the boundaries. Basically, these are abstract solutions to abstract problems. So they're really agnostic to any sort of technology or a scope. They can be used anywhere. You can even use a statecharts to model the problems you have in the nature or in day-to-day life. But they can be used everywhere. I once used it for modeling a CI pipeline in Node.js, for example. And we're working on that. I know that one of the plans of Stately is to later on tackle the area of workflows. And that can be pretty useful for backend systems.
And there's also, you can model anything with it. Like Gatsby use it to model their build process, for instance. So all the node processes and simultaneous things that are going on in a Gatsby build are modeled with XState. But yeah, really, I mean, I've put state charts in Node lambdas before. You can one of the folks in our state Discord used it to. I'm going to get this wrong, Rob, so I'm sorry, but he used it as a kind of connector between a Steinway piano and like a live app that allowed you to play the piano. I mean, if there are events involved, which usually even if you don't call them that, there are always events involved, then state charts will be useful.
Yeah, one more question. In what situations is a state charts overkill, or when it's too much? Is there such a case?
My biased brain would be never, but Basically, if you don't see the complexity of, I mean, any system will, by experience, I'm saying that any system will eventually get complicated. So you're better off managing everything with the state charts at first. We even have a term informally calling stateless state charts, which are basically just objects that are handling events. So I would make my life easier and start using a state chart. And if you're really worried about the bundle size or everything, XState version 5 is going to tackle the tree shaking and stuff like that. And you can also use XState/FSM, which is around 1 kilobyte only, if that's the concern.
And if you want to, sorry, Juho.
Yeah, please go ahead. Yeah.
If you want to, if you consider it overkill to include it in your app, if your bundle size is really sensitive, then use state charts to power your tests. Then you can still verify everything that you're doing through state charts, but not having to include XState in your bundle.
Or even use it for documentation,
Yeah.
as a PR description. Just tell people what your intent of change is.
Sort of related are the projects where Redux flags is more appropriate than state machines.
It always boils down to the team preference. So if your team prefers that and understands that better, because this is just one of the aspects. Engineering is only one dimension. There's a lot more happening in engineering teams and corporations. So consider everything and do the actual engineering yourself.
Mm-hmm. Mm-hmm. Given that team preferences are completely the same, if everyone knew XState as well as they know Redux, Redux is kind of a it uses events in the same way. It uses a single global store, and it uses reducers instead of finite state machines. So it's kind of like XState but smaller. So if that is a good way for you to encompass your app's logic and you're happy with that, then yeah.
All right, so maybe we can do a round of takeaways. So what are the points you took with you from this session and this kind of stuff? So maybe Laura, you have some.
Yeah, I will start with that. I think that state charts are really so beneficial in terms of collaboration. They're going to make it easier to not just write your code, but to share your code and to be able to share what you're working on with the rest of your team of any discipline. And so it's going to make a huge difference to everything you do in that way, because so much of what we do is actually communication rather than writing code.
Yep, and having that communication just built in with just as you're building your code, I think that's really fascinating. Something that really excites me is being able to build out tooling that makes that easier, more visual, and allow it to be brought earlier and earlier in the process. So when you're using state charts, should really be the one of the first things you build, even pre-design. If you're using your state charts to power your understanding of your app, even in the spec stage, then yeah, possibilities are endless.
Yeah, if I were told like a few years ago, actually at the beginning of my career when I was a junior developer, that there's a vacation and can even help you understand your own code, then I would have learned it from the beginning. So do yourself a favor and teach it to juniors at your companies too. They will really thank you later on in their career.
That's such a good point.
Yeah. All right, so I guess now we have a lot of people going to try state charts and state machines and get really excited. And I hope we have in next React Finland, we have a session as well, I hope. So thanks a lot, everyone. It was a great session, and bye.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.